So let's see how much of these you remembered. And I know I did throw a twist in there, a couple of them. First thing I asked you to find is the median. To find the median, what are the two things we have to do? Well, to find the median, first thing we have to do is make sure they're put in order from smallest to largest. And they already are. The second thing we have to do is find the position. To find the position of the median, we need to know how many are there. In other words, n. What's n for this set of numbers? N is going to be 5. Perfect. Why is it 5? Yeah, because there's 5 numbers in the list. That's why n is 5. Perfect. N is just the number of items in the list. So now to find the position of that median from n, we're going to do 0.5 times n. So 0.5 times 5 is 2.5. So our position is 2.5. What does that tell us? Now remember we said there's two possibilities. If one possibility occurs, it's between that position and the next position. If the other possibility occurs, it's you round it and it's in that certain position. So what do we do here? This one, since it comes out to be a decimal, since it comes out to be 0.5, we round up. It's going to be the third number in the list, which is the 18. So the median of this set of data is 18. Next step, the mean. How do we find the mean? We add them all together and divide by the number that are there. We divide by n, which is 5. And when we do that, we should get 18. I believe, right? How many had 18 for both of those first two so far? Okay. Now the first loop I threw you, by the way, is I put the median first. Usually we're used to doing the mean first, so hopefully you caught that. Those are the measures of center. Now remember, the third measure of center is mode, which is the number that appears most often. But in a small set of data like this, there's very seldom are there numbers repeated. So this set has no mode because there are no numbers that are repeated. Now the question always comes up, well, what if there are two different numbers that are repeated? Is it possible to have two modes? That depends on what textbook you're looking at. Some textbooks will say that a data set has one mode or no mode. Some textbooks will say it can have up to two. Other textbooks go through some fancy formula of, it depends on how big the data set is. It's the square root of n minus 1 or whatever, and that's how many different modes it can possibly have. For this class, in order to keep it simple, there's either one mode or there's no mode, period. Now for the range, how do we find the range? It's the largest number, which is the 24, minus the smallest, which is 11. Gives us a range of 13. How many of you had 13 for the range? Good deal. Now before I do the standard deviation, I'm going to jump down and do the mid-range. The mid-range, I realize is something we did not talk about on Tuesday. Sorry, I don't know why I can't stop yawning. It's one of the lesser known measures of center, actually. Yeah, I know, I'm so boring I put myself to sleep. One of our lesser known measures of center, and what it is you just take the largest plus the smallest and divide by 2. So 24 plus 11 is 35, divided by 2 is 17.5. Notice it's very close to the 18 that we had for both the mean and the median. In a good set of data, remember we talked a little bit on Tuesday about a good set of data and a bad set of data. In a good set of data, and by good I mean normally distributed or close to normally distributed. In a good set of data, the mean and median will be equal, and the mid-range will also be equal, and so will the mode. They'll all be the same number. Obviously here the mid-range is a little bit different from the mean and the median, so this is not a great set of data. It's not a bad one because they're close, but it's not a great set of data because they're not the same. So let's take a peek at that standard deviation thing that we've got to do. For the standard deviation, what is step 1? Step 1 is to find what? Mean. There we go. Find the mean, which we found to be 18. Step 2, that is to do what? Subtract. You got it. So from each of those numbers, 11, 16, 18, 21, and 24, I am going to subtract the mean of 18. So 11 minus 18 was -7. 16 minus 18? -2, yeah. 18 minus 18? Sorry, 0. 21 minus 18? 3. And 24 minus 18? 6. Now if I were to add those up, what should they equal? 0. Very good. And as we said, that's not something that you need to do, but it is one way of double checking your work. What is step 3? Square each number. So -7 squared is 49. -2 squared. 4. 0 squared. 0. 3 squared. 9 and 6 squared. 36. Wonderful. Step 4. Find the total. Which does come out to be 98. You are correct. And then step 5. Divide. Why am I dividing by 4? So we're dividing by n minus 1. Since n is 5, 5 minus 1 equals 4. So what do we get? 24.5? Yes? No? That would be the variance, by the way, if we were ever asked to find the variance, but we weren't. So what do we have to do to find the standard deviation yet? Square root. Very good. Square root of 24.5 is 4.9, what? 4.91? 4.95? Okay. How many of you had 4.95 for your standard deviation? Good. How many are confident you can do that on a test? Like maybe Tuesday? Okay. No hints there at all. You think? Yeah. Who knows? Okay, so now that we can find standard deviation, mean, median, all that stuff, what are they good for? We talked about how they describe that bell curve, that normal curve. They tell us on our number line where the center is, and then approximately how wide the curve is. But what good does knowing that do us? Well, if we know the mean or the median and the standard deviation, there's a lot that we can say about a set of data. Under a bell curve. I know, it's annoying me, so I'm sorry about the yawning. I'm going to have to give in and hit some caffeine. Under the bell curve, we said the center of the curve is always the mean or the median. We're going to use the mean, just because that's what's usually used. The mean and the median should be the same if it's truly a normal curve. Mine's a little lopsided, but it's okay. Pretend it's symmetrical. We go out in standard intervals. The length of those steps is one standard deviation. So this would be -1 standard deviation. This would be -2 standard deviations. And -3 standard deviations from the mean. We talked a little bit on Tuesday about something called outliers. We talked about it a little bit with our example with Ralph Sampson making the multi-million-dollar contract, and what that outlier does to the data. Generally, nearly all the data will fall within 3 standard deviations of the mean. Anything more than 3 standard deviations away from the mean is considered an outlier, considered unusual. If you're in manufacturing, anybody here come from a manufacturing setting where they ever heard of something called 6 Sigma? No? It's a quality control system that's often used in manufacturing. Of your quality control people keep track of your production, and if your size of your parts or weights of your parts or something that you're monitoring falls outside of 3 standard deviations from the mean, then it's considered to be a problem with the machine. You got to figure out what happened. Why did it get so far away? The reason it's called 6 Sigma, by the way, Sigma is the symbol. Sigma looks like this. That's the Greek letter S, basically. Sigma is the symbol that is used to signify standard deviation. You guys don't need to know that, but it's called 6 Sigma because you go 3 standard deviations below, and then of course the next thing we're going to do is we're going to go 3 standard deviations above. So +1 standard deviation, +2 standard deviations, and +3 standard deviations. And of course anything out here would also be considered an outlier. Well, the cool thing is on this curve, if you lay out the mean in the center and you go out adding a standard deviation as you go this way and subtracting the standard deviation at each step going that way, if it is truly a normally distributed set of data or close to a normally distributed set of data, the amount of data that falls within each section is very, very predictable. Now I've got to remember whether your book uses the exact or the approximate. I'm going to look it up just to be safe. So this will be in chapter 9. Right? Actually, probably not. There's 2 types of curves. There's the approximate bell curve and there's the exact bell curve. And I don't want to confuse you by doing something different than what your book does. Okay. So, between the mean and 1 standard deviation below, 34% of the data falls in that range. This is the approximate one. Those of you that go on to take business math, by the way, the business math textbook uses the exact. So it's like 34.13 or something like that is what they use percent. Since this is symmetrical, it's 34% between the mean and 1 standard deviation above the mean as well. If we keep going, 13.5% of the data falls between 1 and 2 standard deviations on each side. And then between 2 and 3 standard deviations is 2.35% on each side. Had I drawn my curve symmetrical, those sections would look the same. And then outside of 3 standard deviations, it is 0.15%. What that means, 0.15% out here means that if you produced 1,000 parts, if things were operating correctly, out of 1,000 parts, you'd expect less than 1.5 parts to go over that measurement, and less than 1.5 to go below this measurement. So if you think about that in quality control, that's a big issue of if we start getting several of them that are beyond one of those points, then it's statistically very unlikely, which means there's most likely a problem with the machine. But right now you're probably looking at this and saying, where did those percents come from? Those percents are actually standard. Those percents stay the same. You'll notice right now there are no numbers down here. I just have them labeled as 1 standard deviation and 2 standard deviations and stuff. The key is the numbers that go on the bottom down here change depending on the data. For example, let's say that I have a set of data that, well, let's say I'm producing parts, and the mean length of part is 280 millimeters. And the standard deviation in my production is 2 millimeters. What that means, the mean here in the middle is 280. What's going to go here? If I subtract 1 standard deviation is 2 millimeters. I'm going to get 278. The mean of 280 minus 2. If I go here, I'm going to subtract 1 more standard deviation. What's that going to be? 276. Perfect. And here? 274. Going the other way, if I start at the mean of 280 and I add a standard deviation, this is going to be 282. This will be 284 and 286. Perfect. So what this is saying is, if I spend the day producing parts and I look back on the parts I've produced for the day, if that machine is operating normally, I will expect 34% of the parts produced to be between 278 millimeters and 280 millimeters long. I would expect another 34% to be between 280 and 282 millimeters long. I would expect 13.5% to be between 278 and 276. Another 13.5% to be between 282 and 284. Does that make sense? So if I asked you what percent do you expect to be larger than 278 millimeters? Where's 278? That's right here, right? So that's my 278 millimeters. Larger than that would be up this way, right? So to find what percent is larger than 278 millimeters, I just add all those percents together. If I add them together, I should get 84%. Everybody see where that 84 comes from? Any questions on it? I'm just going from my 278 and I'm adding up all the percents that are on the larger side of it. What if I were to ask, what percent do you expect to be smaller than 284 millimeters? Well, here's 284. Smaller than would be left or right? Left. So I'm going to add up those percents. You get 97.5% if I add them all up. Does that make sense? Well, outside of manufacturing, how could this be useful to you? Well, let's say you go to buy a house. You're going to move to a new area and you're not really familiar with house prices in that area. So you do some research and you find what you're looking for is you're looking for a 3-bedroom, 2-bathroom house. And what you find is in the area you're looking, the mean price is $148,000. And the standard deviation is $21,000. So what does that mean? That means if we draw this bell curve, what number is going to go at the center of this bell curve? 148,000. I'm just going to put 148 there just to save some room. If I go one notch over, what percent goes in here, by the way? 34%. The percents never change. What's going to go here? 127. Where'd the 127 come from? Well, I have a mean of 148 minus the standard deviation of 21,000. I'm subtracting the standard deviation each step. My next step, what's this number going to be? $106. I subtract another 21,000. What's the percent going to be in here? 13.5. That percent, again, never changes. Over here, what number is going to go down here? 85,000. This percent is 2.35%. And of course, only 0.15% would be less than 85,000. Going this way, what number would I put down here? 169. Take the 148 plus 21,000. This, of course, is still 34%. What number goes down here? 190, adding another 21,000. This is still 13.5%. Right here is going to be 211,000, of course, 2.35%, and 0.15% out here. So you've been looking, and you've looked at a few houses, and you find one that you are just absolutely in love with. It has everything you want, beautiful house, some features that you didn't even know you wanted, priced at $190,000. Your realtor is telling you you better put in an offer on this one right now. It's not going to last very long. But if you look at it, what does this bell curve tell us about that $190,000 price? Well, $190,000 is right here, right there. And if we look at these percents here that are below that, if we add those up, that adds up to 97.5%. What's that 97.5% mean? Well, that means of all the 3-bedroom, 2-bath houses in that area, 97.5% of them are cheaper than the one that you just looked at. So do you think that means there's a good chance you're going to find another one you like that's cheaper? Most likely. 97.5% of them are cheaper. There's a good chance in that 97.5% there's going to be one that you like. On the flip side of that, if you were selling a house and you figured your house was middle of the road, would you accept an offer of $125,000? Well, that's somewhere right in here, right? You said you figured your house was middle of the road. 68% of them, 34 plus 34 makes 68%. 68% of houses, the middle 68% of 3-bedroom, 2-bathroom houses in that area sell between $127,000 and $169,000. If I thought my house was middle of the road, I would not accept anything below $127,000. Because my house is definitely in the middle, 68%. So that $125,000 offer is out the window to me. Does that make sense? So let's say that you go to a new area and you've got a couple of different job offers. You are offered in this new area a starting wage of $12.70 per hour. In that area, the mean starting wage is $11.40 per hour, with a standard deviation of $1.30 per hour. Is that a good offer? I want you to take a second and think about it. Maybe draw out the bell curve, and we'll talk about it in just a minute. So if I draw out my curve here, I don't even really need to do the whole thing. The center of my curve is going to be 1140. The mean always goes at the center. If I go one step this way, I'm going to be subtracting the 130. This will be 1010. Going one step this way, it would be 1270, which is what I am being offered right there, right? This percent here is 34%. Now, I'm not going to fill in the percents over on this side. What do I know these percents have to add up to? 50%. How do I know that? It's half the curve, right? Symmetrical. Half of 100% is 50%. So that starting salary, that starting wage of $12.70 an hour is better than 87% of people in that area. I would probably be happy with that. Not 87, 84%, sorry. 84% of people in that area. Still, I'd be happy with that. Another way to use this mean and standard deviation is to compare things. Something called the Z-score. A Z-score compares when we're used to compare two numbers that can't necessarily be compared with each other. For example, all of you took an entrance test to get in here. You may have scored a certain score in reading and a certain score in math. Well, how do you know whether you did better in one or the other? Well, you had a higher number for reading. Does that mean you were better at reading? Not necessarily. Because you don't know whether the reading test was harder or easier than the math test or how it compares. So what they do is they compare them back to their own set of data in order to compare them to each other. They find their position within their own set of data. And that's what a Z-score does. is it measures position within its own data. And the way a z-score is calculated is you take the number, you subtract the mean from that number, and you divide that difference by the standard deviation. And what that does is it finds how many standard deviations above or below the mean that number is. Now you'll see that's very similar to our bell curve, because on our bell curve we're looking at comparing where the standard deviations lie in the percents and stuff. It really is, it is using the bell curve, we're just not using that empirical rule or those percents that we have been. For example, let's say that you are selling your house and you get an offer of $138,000. And we're still using that mean from up here. We had a mean of 148. 148,000. And a standard deviation of 21,000. Our z-score is going to be found by taking the 138,000. Wow, I can do that right today. 138,000, which is our number, minus the mean of 148,000, divided by my standard deviation of 21,000. So 138,000 minus 148,000 is a negative 10,000. Divided by 21,000. Unit 0.476, we're going to call it. Negative. Well, this is telling us two things. One, the negative is telling us that this is below the mean, below average. The 0.476 is telling us that this is 0.476, or less than half a standard deviation below the mean. So you're below average, but not a long ways below average. So that means you have to decide, is your house average or better, or slightly below average? If it's slightly below average, that's probably about the right price for your house. Most of the time, however, a z-score isn't used for just a single number. It's used for comparing two different numbers. So let's say that you found two houses in two different neighborhoods. House A has a list price of $152,000. It's in a neighborhood with a mean price of $138,000 and a standard deviation of $7,000. Well, that makes it two. Yeah, we'll do $7,000. $7,000. House B has a list price of $168,000. It is in a neighborhood where the mean price is $148,000 and the standard deviation is $12,000. Now you might look at that and say, well, gee, the $152,000 compared to $168,000, that's cheaper. And you might even say, well, this one's $14,000 above the mean. This one's $20,000 above the mean. That still seems to be that this one's a better deal. But you got to remember, it's in different neighborhoods where the value might be different. So if you look at this, we're going to find a z-score for each. The z-score for this first one is going to be found by doing what? 152,000 minus 138,000. Divided by what? 7,000. Good. So we subtract 152 minus 138 is 14,000. Positive or negative? Positive. Divided by 7,000 is 2. That's telling us that this house is 2 standard deviations above the mean for houses in that neighborhood. So over here, let's find the z-score. How are we going to find this z-score? Perfect. 168 minus 148 divided by 12. What's 168 minus 148? 20,000. Positive or negative? Positive. Divided by the 12,000, which is 1.67. That house is only 1.67 standard deviations above the mean for that neighborhood. So technically, this one's a better deal. This is a more expensive home compared to the homes in its neighborhood. Does that make sense? So let's go back to your reading and math scores on your tests. We're going to put math first where it belongs. And let's say for math you scored a 52. And for reading you scored 74. But for all people who took the math test, let's say the mean is 72, the standard deviation of 16. For all people who took the reading test, let's say the mean is, let's see here. 88 with a standard deviation of 8. I want you in your notes to find the z-scores for each of those for me and tell me which one is a better score. So for our first one here, what'd you get for a z-score? 1.25. So it's 52 minus 72 over 16. 52 minus 72 is a negative 20 divided by 16 is a negative 1.25. The negative is important there because that tells us that this is below the mean. So on the English or in the math test, you scored 1.25 standard deviations below the mean. On the English test, what'd you get? What's that? 1.75 negative. So let's take a look. So 74 minus 88 over 8. 74 minus 88 is a negative 14. Divided by 8 is a negative 1.75. So on the reading test, you scored 1 3/4 standard deviations below the mean, or 1.75 standard deviations below the mean. So which one did you do worse on? Reading. Now, I'm not saying those numbers are real by any means, but it's a way to compare. Another good example might be let's say you get into an argument looking at high school basketball players. Let's say that there's one high school basketball player, male player, who is 6'9" tall. And you think, boy, he's really tall, he's a real asset. But then you're looking at, you have a female player who is 6'1" tall. So another person claims that she is actually the bigger asset with her height on the women's basketball team. Let's say now we're not looking at the mean of all males, we're looking at mean height of male basketball players in high school. Let's say the mean is 6'0" with a standard deviation of 4 inches. For females, the mean is 5'6" with a standard deviation of 3 inches. Which one is more unusual, a taller player compared to their population? I'll give you a minute to look at that one. Be careful with the numbers here because it's written in feet and inches. You might have to do some converting or whatever to make it work. So for our male player, do the z-score. I'm going to convert 6'9" to 81 inches. 6 foot into 72 inches. So now my z-score will be 81 minus 72 divided by 4. What'd you come up with? 2.25. Very good. So that male player is 2.25 standard deviations above or below? Above, because it is positive. Our female player, z-score, is going to be found. Well, I'd convert 6'1" into 73 inches, 5'6" into 66 inches. So what are we going to do there? (73 minus 66) over 3. Yep. 73 minus 66 is 7 divided by 3 is 2.33 positive. So who is actually taller compared to their own population? The female player is. Put them side by side, they're not taller, but again, if you're looking at what is the more unusual height compared to the population they're drawn from. This can be used to compare, like we said, starting minimum wages. It can be used to compare home prices like we did. When we come back from break, we're actually going to use it on an example to see if you can make a managerial decision based on it. So anyway, go ahead and take our break. It is 9:59. We'll come back at 10:09.